This video will demonstrate how to use an extended version of the algebraic method to properly balance a redox reaction. And this example uses one that is done in an acidic solution. So if this is done in an acidic environment, that means that we can assume that we will have H plus and H2O. So I can arbitrarily add these to one side of the reaction or the other, as long as I follow through with the remainder of the algebraic method, which requires me to place dummy coefficients on everything, D, E, F, and G. And then, using the dummy coefficients, I write equations for every element, as well as, and this is the extension, the charge. So I will have one for chlorine, I'll have one for tin, I'll have one for nitrogen, oxygen, and hydrogen. And finally, I'll have one for the charge. So now we simply step through in the usual way. A equals 6D. For tin, we have B equals D. For nitrogen, we have C equals E. For oxygen, we have 3C equals 2E plus G. For hydrogen, we have none as reactants, and this is perfectly okay. That just means that 0 will equal whatever we count up for our hydrogens, F plus 2G. And for the charge, A will give us -1, so every copy of that counts. C also adds to the negative charge. We have a -2 times D, and plus whatever we get from F. So now that we've written out the equations for all of our elements plus the charge, we can go to the thinking step where we line up all of our variables, A, B, C, D, E, F, and G, and we have to determine which one we can use to allow us to capture everything else. If we pick a value for E, this gives us a value for C. If we have values for C and E, we can solve for G. If we have G, we can get F. Now, that means then that we will have values for C and F. A and D have a relationship, so we can substitute in and solve that way. So I'm going to make the choice to let E be equal to 1. This means that C is now equal to 1. And we now have values for E and C. So 3 equals 2 plus something. That means that G is also equal to 1. 0 equals F plus 2G. G equals 1, so F plus 2 equals 0. That means that F has to be a -2. More on this later. So now we have values for C, E, F, and G. We're going to use that information in our charge equation to find a better solution. So I know that A equals 6D, so I can substitute in 6D. C equals 1 minus 2D plus F, which is -2. So now I can group everything on the same sides, and I will ultimately have 1 equals 4D. If 1 equals 4D, then D must equal 1/4. B and D are also equal to each other. And A equals 6 times D, so that would be 6/4. And the reason I don't simplify that is because in the algebraic method, when we're left with fractions, we're going to multiply everything to get rid of it. So by multiplying everything by 4, I have A equals 6, B equals 1, C equals 4, D equals 1, E equals 4, F equals -8, and G equals 4. So at this point, I have to go back and actually fill in everything. To do that, I'll need to erase all of this and rewrite the equation with these coefficients. So A equals 6, B equals 1, C equals 4, D equals 1, E equals 4, F equals -8, and G equals 4. In the interest of space, I'll erase these guys. So I have -8 here and 4 here. So now the only thing that's wrong is that everything is in a whole number ratio, but they're not all positive numbers. In order to fix this, I will add 8 hydrogen ions to both sides. By doing this, it allows me to get rid of the -8 moles, because these two will cancel, effectively moving the 8 hydrogens to the other side of the reaction. At this point, I can write out the completely balanced redox reaction, and it will be left to you, the viewer, to verify that this actually worked and that we have a reaction that is now balanced in terms of the matter as well as the charges. And so this extension to the redox half reaction method, by balancing it using the algebraic method, requires that we can respect having negative values and know how to move them from one side of the yield zero to the other.